Hello, I'm Himan Namdari from Worcester Polytechnic Institute Data Science Department, and today I'll share our research on GPR signal analysis via descriptive statistics and machine learning. I'd like to thank Dr. Zakavat, Majid Moradikia, and Dr. Petke from WPI Physics, and Dr. Askari from Michigan Tech Geophysics Department, and I am thrilled to share our finding with you all today. Suboptimal irrigation can hurt our food supply. It can cost farmers more and damage the soil. It wastes water and nutrition and even stresses the plants. To create optimized model and water crops correctly, farmers need up-to-date data from the root zone, which can be anywhere from 5 to 150 centimeter deep in the soil based on the crop type. If farmers use better model, they can water their crops based on real measurement and what's happening beneath the soil. And this can lead to a better farming and productive agriculture. A tool that gaining attention for this task is air-coupled ground penetration radar system. This device can send a wave into the soil and reads the signal that bounces back. And this technology can help farmers to know things like how wet the soil is in the root zone, and they can update their irrigation model based on these information. Air-coupled GPR stands out for its non-invasive method, quick data collection, and safety, but its uses aren't limited to just one field. In forestry, it helps to gauge the soil moisture, which can tell us about tree health and the forest overall condition. For civil engineering and construction, soil moisture can influence the structure, strength, and stability. In assessing wildfire, the moisture estimation reduces the risk of wildfire itself. And even beyond our planet, in the space exploration, understanding soil moisture can hint at the presence of water and give insight to other planetary conditions. Now, let's dive into how GPR works and how it can help to estimate the soil moisture in root zone. GPR is a radar, which, as we mentioned before, it sends an electromagnetic wave down into the soil. You can see an example of GPR radar and a time domain representation of the received signal on the top figure. Now, see the bottom figure. When these waves hit changes in the soil, like different layers or moisture level, they basically bounce back. Why? Because something called permittivity, which is actually the capability of the soil for holding electrical energy. Different layers in soil, which are getting distinct by different moisture, make the GPR signal to have noticeable peak, as you can see in the time domain plot in the top figure. The first peak is related to the direct wave from the transmitter to receiver, and the second wave is actually the second wave received from the first layer. This is a representation of one layer model, but with any number of layers, we can have the same number of reflection, as can you see in the figure over here. GPR collects data mainly in two ways, surface couple and air couple. Looking at the top figure, you'll see surface couple, but there is a catch. It can disturb and damage the soil, and it covers less area and takes longer. Now, check out the bottom figure, which we are showing an air couple method with the GPR radar has been coupled to a drone. It's going to be gentler because it doesn't touch the soil at all. And what makes it more standing out is the speed and the ability to cover vast areas. This makes air coupled GPR a perfect tool for collecting data in big farm, which was one of our primary goals. Now, let's dive into principle behind the GPR. A key idea here is an equation called skin depth, as you can see the equation over here. Here, delta represents the penetration depths, and gamma represents the angular frequency. Epsilon is the permittivity of the soil, and mu is the permeability. So the wetter the soil, we can expect higher permittivity. And as you can see with the indirect relationship between them, when the soil is more wet, you have lower depth of penetration. Keep in mind that for most soil, permeability stays the same. So the depth waves can penetrate is mainly influenced by frequency and permittivity. Now, we know and mentioned that working with a vast amount of GPR data is not going to be a simple task. That's why simulations, especially GPR Max, are becoming so popular. What is GPR Max? It's a top-notch open source tool for simulating GPR signal. Its strength lies in a finite difference time domain method that ensures the simulation data is as close as possible to the real-world scenario. You can see a 1 or 2 or 3D representation of the simulation generated by GPR Max. For our work, we leaned heavily on GPR Max to generate synthetic data, and we simulated different soil conditions by zooming on moisture level and depth changes. We specifically work with the AScan or time domain representation of the data, and you can see one of these examples on figure top left. Now, collecting and handling GPR data brings up two big challenges. First, there is a data complexity, which comes from the soil by nature is complex, and we collect a large amount of these type of data. Next, the labeling process. Traditionally, we rely on experts to label the 1D or 2D data generated by GPR radar. But getting this label right is crucial, especially when we want to use this type of data to train a machine learning model. So we did tackle this issue first by using GPR Max that lets us generate synthetic data with their labels, and also to extract more useful feature, we proposed the feature extraction by using a descriptive statistics, as we mentioned before. And later on, we used machine learning model to find and select the most important features among the extracted features by our proposed method. Changing soil property can change the behavior of the received signal. That's the key point in our experiments. We wanted to see changing the permittivity or the depth of the soil, how it's going to impact our the shape of our signal, the amplitude pattern of our signal. It could possibly generate an anomaly in our signal, and it's definitely will create some delays. And change in frequency component also can create different phenomena in our received signal. So we can use these variations and changes in our signal to estimate soil moisture, as we discussed before. Now, there are many ways to extract model features from the GPR signal. These methods could be considered as wave-led decomposition, which is basically breaks down the signal into different frequency part. The PCA reduces the data dimension for easier handling. The frequency analysis shows how signal change over time and across the frequency. And simple statistics and texture analysis uses basic like mean and variance to spotlight the data trends. But among these methods, descriptive statistics stands out for several reasons. It has low complexity, and it also has high efficiency, while it's adaptable for different type of data. And this will help us to find more related feature to our prediction task. Those features could be mean, STD, kurtosis, and quartile percentile, as we used it in our proposed model. Here you can see a snapshot of our process in this project. We created large realistic model mirroring real condition using GPR Max. That gives us a data set of 10,000 by 1968 samples each, generating diversity in simulation by adjusting aspects like permittivity, layer depths. Each dataset is tailored to a unique condition. Model label could either be uni or multi-label, where these labels are permittivity and layer depth value in the model. We then process each AScan dataset and extracted the 15 features by descriptive statistics, and then we fit this data into a random forest model using regression task to extract and select the top most important feature from our data set. And the general methodology, as I kind of like mentioned before, was generating different soil scenarios, analyzing the impact of these variables, and using the raw data to extract the main descriptive statistics features, and usually using random forest to reduce them down to a smaller size. And at the end, we evaluate our method by using a neural network model, and we train the model using raw data with respect to our extracted 5 top features. So for descriptive statistic, as we mentioned before, we extracted features like mean, max, a standard deviation, and quartile percentile using Python, and we save this data into a CSV file, and later on we use this data for further feature selection. In the frequency domain, we also focused on key traits like mean, max, and the standard deviation, and the reduction size for this approach was almost 99%. And for the next step, we used the 15 feature extracted from our GPR signal and fit them into a random forest model to find the top 5 important features. Random forest is a supervised machine learning technique that ranks the importance of the feature by evaluating the Gini impurity in classification and mean square error in the regression task. Lower the impurity, or MSE, means that the feature is more important and can improve the prediction accuracy. For our experimental setup, we had 2 type of model, 1 to 3 layer model. The dimension was 1.5 meter by 2 millimeter. It was a 3D model. The propagation time was set to 5 to 8 nanosecond. Frequency was set to 1.5 gigahertz. And we used a Ricker waveform as one of our most common waveform used in GPR analysis. And also the permittivity and depth has been varied, as you can see, from 2 to 78 for permittivity and 1 centimeter to 10 centimeter for depth. So we first tested the impact of permittivity on GPR signal, keeping all other factors constant. We just varied permittivity. As you can see, as permittivity goes up, over here in this equation, the velocity of the signal will be reduced. Basically, higher permittivity means slower signal propagation, stronger reflection, and delayed reflection on the arrival. Also, the signal will be attenuated faster and higher permittivity level. For our next experiment, we analyzed the impact of depth, and we varied the depth between 1 centimeters to 10 centimeters. Again, we observed high attenuation, slower signal propagation, and the signal were attenuating faster by the depth level. For the last experiment, we analyzed the impact of frequency, varying between 0.5 to 2 gigahertz. And the result shows that higher frequency are more interpretable. As you can see the reflections are more clear with respect to the half gigahertz frequency. And at the same time, a higher frequency can impact the depths of penetration and signal attenuation as well. After extracting the 15 feature by using the descriptive statistics method, we actually try to check the relationship between these features and varying the permittivity. As you can see, as a result, the skewness, standard deviation, quartile percentile 3 and 4 had a direct positive correlation, while quartile percentile 2 and 3 exhibit an inverse relationship with permittivity changes. And mean and max values were less straightforward. So these findings highlight the relationship between permittivity and descriptive statistic features as we extract them. The RF model identified Q4, FFT, and peak mean, kurtosis, and skewness as the most important feature. As you can see in the figure on the right, these features has been selected with the highest importance in the prediction. These reflects the distribution and frequency component and asymmetry of the GPR signal that can be affected by soil properties like moisture. We later use a correlation matrix to analyze the relationship between these 15 features that we extracted. And furthermore, we can use the combination of these two approaches to narrow our size of features down. In conclusion, using GPR Max, we estimated and generated varied soil model to build a label dataset. We then streamlined over 1,600 features to a Widal 15, and using a random forest approach, we reduced this size to 5 critical features. The method reduced data size by 99%, yet remained efficient in terms of root mean square error in prediction. As you can see in here, the root mean square was not increasing much, and it's not impacting, and this amount of increasing is not impacting our soil moisture prediction due to the fact of permittivity changes. So our data size cut was 99%, and the most important part was the execution time of the model. The feature extracted by our proposed model was trained 98% faster than the raw model. Thank you so much for listening. I hope this was a useful and informative presentation. I hope that you're having a good day. Thank you.